after running your test suite in Claude Code. Your entire conversation context is filled with thousands of lines of test output. 90 tests passed and 10 failed. But now you're carrying all 90 useless passing outputs in your context. Your next request will be slower and more expensive because Claude has to process all that noise. This is exactly the problem that subagents solve. They're specialized AI assistants that work in isolation, keeping verbose output out of your main conversation. They're fundamental to efficient Claude Code workflows when you understand how to use them. In this video, you'll learn everything you need to master subagents. We'll cover the built-in subagents that Claude uses automatically, how to create custom subagents for your workflows, and the core patterns that make them powerful. We'll also dive into advanced features like persistent memory and conditional tool restrictions with hooks. By the end, you'll know exactly when to use subagents, how to configure them, and how to avoid common pitfalls. Context is your most precious resource when working with AI coding assistants. Claude Code has a large context window, but it's not unlimited. And every token you fill with irrelevant information makes your session slower and more expensive. When you run operations that produce verbose output, you face a choice. You can run them in your main conversation where all that output stays in your context, or you can isolate the work in a subagent where only a summary returns to you. The difference is massive. Let's make this concrete with a test suite example. If you run 100 tests where 10 fail in your main conversation, all 100 results fill your context. The 90 passing tests provide no value, but they're consuming space, and every subsequent request has to process that useless output. A subagent solves this elegantly. When you delegate test running to a subagent, it executes in its own isolated context, analyzes all the results, identifies the failures, and returns just the critical information. Those 90 passing tests never touch your main context. This pattern applies to any high-volume operation. Log file analysis, code base exploration, documentation fetching, dependency tree mapping, any operation where you only need a summary is a perfect subagent use case. The principle is simple. Isolate the noise, preserve the signal. Claude Code comes with 3 built-in subagents that it uses automatically when appropriate. Understanding these gives you insight into when Claude delegates work, and you can invoke them explicitly when you want specific behavior. The first is the Explore subagent, which runs on Haiku for maximum speed and cost-effectiveness. It's optimized for read-only codebase exploration, with access to read, grep, glob, and bash, but it cannot write or edit anything. Explore has 3 thoroughness levels: quick for targeted lookups, medium for balanced exploration, and very thorough for deep analysis across the entire codebase. The second is the Plan subagent, used during plan mode when working through large changes. It has the same read-only restrictions as Explore, but uses your main conversations model instead of Haiku, giving it more capability for complex reasoning about architecture. The third is the general-purpose subagent, which has access to all tools, including write and edit. Claude uses this for complex multi-step tasks that require both exploration and modification, and it inherits your main conversations model. You don't have to wait for Claude to decide when to use these. You can invoke them explicitly by saying something like, use the Explore subagent with very thorough search to map all authentication patterns. Custom subagents are where you unlock real workflow optimization by creating specialists tailored to your specific codebase and recurring tasks. The creation process is straightforward using the /agents command. When you type /agents in Claude Code, you get an interactive interface where you first choose between user-level and project-level scope. User-level subagents live in your home directory and are available across all projects, while project-level subagents live in your project's.claudeagents directory and should be checked into version control for team sharing. Next, you choose how to create the subagent. You can have Claude generate it by describing what you want, or you can write it manually. With Claude generation, you describe the purpose, and Claude creates the system prompt and configuration, which you can edit before saving. Then you select which tools the subagent can access. For a read-only code reviewer, you'd give it read, grep, and glob, but deny write and edit. For a debugger, you'd include edit access. You also choose the model: Haiku for fast and cheap operations, Sonnet for balanced capability, Opus for complex reasoning, or Inherit to use whatever model your main conversation is running. Once you save the subagent, it's immediately available. Claude can delegate to it automatically when it encounters matching tasks, or you can invoke it explicitly. The /agents command also lets you list, edit, and delete subagents as needed. Every subagent is defined by a markdown file with YAML front matter. The configuration is simple but powerful, giving you precise control over behavior. The required fields are name and description. The name is your unique identifier, but the description is critical because Claude reads it to decide when to delegate automatically. You should explain when to invoke the subagent, not just what it does. Tool configuration controls what the subagent can access. You can use an allow list to specify exactly which tools are available, or use a deny list to remove specific tools. Model selection determines intelligence versus cost. Haiku for fast and cheap tasks, Sonnet for balanced workflows, Opus for complex reasoning, or Inherit to match your main conversation. Permission mode controls how the subagent handles prompts. Default passes prompts to you. Don't ask bypasses pre-approved operations. Accept edits auto-approves file edits. And bypass permissions skips all prompts for trusted automation. Advanced options include background execution for long-running tasks, work tree isolation for experimental changes, memory for persistent learning, and hooks for custom validation. These aren't needed for basic subagents, so start simple and add complexity when you need it. The first essential pattern is isolating high-volume output, which solves the context preservation problem. When an operation produces massive output, but you only need a summary, delegate it to a subagent. The classic example is running test suites. If you run 100 tests where 10 fail in your main conversation, all 100 results fill your context. The 90 passing tests provide zero value but consume space, and every subsequent request has to process that useless output. A test runner subagent changes everything. You configure it with bash for running tests and read for analyzing results. The subagent executes in its isolated context, sees all the results, identifies the failures, extracts errors and stack traces, and returns just the critical information. Those 90 passing tests never touch your main context. This pattern applies broadly to log file analysis, database queries that return hundreds of rows when you only need aggregated statistics, documentation fetching, and dependency tree mapping. The key is designing what comes back. The subagent should return only actionable information, like test failures with stack traces, error patterns with line numbers, and aggregated statistics, rather than raw data. Implementation is straightforward. Create a subagent with the tools it needs, give it a clear system prompt explaining what to analyze and report, and the subagent handles the verbose work, while your main context stays focused. The second essential pattern is parallel independent research. When you need to explore multiple areas of a codebase simultaneously, and those areas don't need to coordinate with each other, this pattern delivers massive time savings. Here's the scenario. You're building a new feature and need to understand 3 different parts of the codebase: authentication patterns, database schema design, and API endpoint conventions. You could research these sequentially, waiting for each analysis to complete, or you can delegate all 3 to separate subagents that work in parallel. Each subagent gets a focused research assignment. One explores authentication patterns like token management and session handling. Another analyzes the database layer for schema conventions and query optimization. The third examines the API structure for endpoint design and error handling. The critical characteristic is independence. These subagents don't need to talk to each other. Authentication research doesn't depend on knowing database details, and API analysis doesn't require coordination with auth patterns. This complete isolation is what makes parallel execution efficient. When all three complete, you receive three summaries. Your main conversation synthesizes the findings and uses that knowledge to design the new feature. You just compressed three sequential research tasks into one parallel operation. Instead of waiting 20 minutes for sequential research, you wait 7 minutes for parallel execution. Implementation uses Claude's ability to spawn multiple tasks concurrently with a single request. And the key is ensuring the research areas are truly independent. The third essential pattern is the sequential workflow. Sometimes you need a multi-step process where each step builds on the previous one, but you still want the isolation benefits of subagents. This pattern chains subagents together through your main conversation. The workflow is simple. Your main agent delegates to subagent 1 with a specific task. That subagent completes its work and returns results to main. Your main agent processes those results, makes decisions, and delegates the next step to subagent 2, which builds on step 1's findings and returns its results. A concrete example is a code improvement workflow. First, a code reviewer subagent analyzes recent changes and identifies performance issues. Maybe it finds inefficient database queries, unnecessary re-renders, and blocking synchronous operations. It returns this analysis, and your main agent processes the findings and prioritizes database optimization first. Next, you delegate to an optimizer subagent with the task of optimizing those queries. The optimizer analyzes them, implements more efficient versions using proper indexing and query structure, and returns the optimized code. Your main conversation receives the changes and can proceed. The key difference from parallel research is the dependency chain. Each step depends on the previous step's output, so you can't run them in parallel. But you still get isolation benefits. The verbose analysis from the reviewer stays in its context. The detailed optimization work stays in the optimizer's context. And your main conversation only carries the essential information. This pattern works for any multi-step process, like research then implement, analyze then refactor, or test then debug. Each step is delegated to a focused subagent, while your main conversation orchestrates the flow. The first advanced subagent feature is persistent memory, which enables subagents to learn across conversations and build institutional knowledge that improves over time. It's powerful when you have recurring tasks that benefit from accumulated wisdom. You configure a subagent with a memory scope, user, project, or local. User memory lives in your home directory and is available across all projects, perfect for general-purpose subagents. Project memory lives in the project directory and gets checked into version control, ideal for team-shared knowledge. Local memory stays in the project, but out of Git for personal notes. When memory is enabled, the subagent gets access to a dedicated directory where the key file is memory.md. The first 200 lines load automatically into every conversation, so you store high-level patterns and frequently referenced information there. Additional markdown files provide detailed notes that the subagent can read when needed. Here's how it works in practice. A code reviewer subagent with user-level memory learns your style and team conventions over time. It documents recurring issues and best practices in its memory. The next time it reviews code, it already knows these patterns and provides more relevant feedback faster. The subagent updates its own memory autonomously. You don't manually maintain these files. After each code review, it adds new patterns or updates existing notes with better context. This creates a compounding effect, where a brand new reviewer provides generic feedback, but after 10 reviews, it knows your naming conventions. After 50, it understands architecture patterns. And after 200 reviews, it's an expert with institutional knowledge that would take a human months to acquire. The second advanced feature is conditional rules with hooks, which let you enforce custom validation logic during subagent execution. This enables sophisticated patterns like allowing powerful tools but constraining how they're used. The motivating use case is database access. You want a subagent that can query your database to answer questions, which means giving it bash access to run SQL commands. But you absolutely don't want it running update, delete, or drop statements. Hooks solve this perfectly. Here's how it works. You create a subagent with bash tool access, but you also define a pre-tool use hook that matches on bash. Every time the subagent tries to use bash, your hook script runs first. The hook receives the proposed command, validates it's a read-only select query, and either allows it or blocks it. If the command contains insert, update, delete, or drop, the hook returns exit code 2, which blocks the action and provides feedback to the subagent. The validation script is simple bash. You read the tool input from stdin, parse out the command, check it against your rules, and return the appropriate exit code. Exit 0 means allow, exit 1 means block silently, and exit 2 means block and show the error. This pattern extends beyond database queries. You can enforce coding standards before file writes, validate API calls before they execute, require approval for destructive Git operations, or check security rules before network requests. The power is in the flexibility. You're not limited to tool allow lists and deny lists. You can allow a tool, but constrain specific uses. Implementation requires writing the validation script and configuring the hook in your subagent's front matter, and hooks are your escape hatch when standard permissions aren't precise enough. If you found this breakdown valuable, hit that subscribe button. This is part 2 of a 3-part series on Claude Code parallel agents. Part 1 covered the fundamental difference between agent teams and subagents. You just watched part 2 on mastering subagents with practical patterns and advanced features. Part 3 is coming next, where we dive deep into agent teams and how to orchestrate multiple AI agents that coordinate in real time. We're building the definitive guide to parallel AI development with Claude Code, from understanding the trade-offs to implementing production patterns. Subscribe so you don't miss part 3 and hit the bell for notifications. If you have questions about subagents or want to share your own patterns, drop a comment below. You now have everything you need to master subagents. We covered the context preservation problem, the 3 built-in subagents, how to create custom subagents with the /agents command, and the 3 essential patterns. We also explored advanced features like persistent memory and hooks for fine-grained control. Subagents are your tool for efficient delegation when you need focused work with isolated output and workers that don't need to coordinate with each other. Start by using the built-in Explore subagent for your next research task. Then create a custom code reviewer or test runner and experiment with the patterns we covered. In part 3 of this series, we'll dive deep into agent teams. That's where you go when subagents aren't enough and your workers need to coordinate and collaborate in real time. We'll cover the architecture, communication patterns, contract-first spawning, and walk through building a complete feature with a 3-agent team. Thanks for watching. Hit subscribe if this helped you understand subagents, and I'll see you in part 3.